Hello, welcome back. In this video, I'm going to be telling you about the Schmidt orthogonalization process. And I'm going to do an example of it also. So before I begin, I need to remind you about the idea of vector projection. Okay, so the general idea here is if we are going to project onto this vector B, suppose we've got a vector like A right here. Okay, I'm going to draw you a picture of the projection of A onto B. Right? It's this vector right about here. It's the component of B, it's part of A in the direction of B. It's also the shadow of A onto B. There's a lot of ways we can write that. But what I'm going to say is that notationally, I'm going to write this as the projection of A onto B. And I'm going to show you how to compute this. Right? But before I show you how to compute it, I will show you what can happen if this is B, and suppose A is headed in the opposite direction, that it's going to be back here. That's going to be the projection. And if A and B are orthogonal to one another, the projection will be the zero vector. And all of this should make sense in terms of the formula that we're about to develop. So to develop this formula, I'm going to go and I'm going to turn this A, B, and red thing into a right triangle and do some trigonometry. Okay. So basically, this is the length of A here. This is going to be the length of the projection, which I'm just going to call the projection for now. And this is going to be theta. Okay. And I'm going to call the length of the projection K, just so I don't have to carry that around with me. What I'm going to say is that K, the length of the projection, is going to be the length of A times the cosine of theta. Okay? But I also know that this A is part of a vector and B is also part of a vector. And we've got this formula that relates the dot product to the angle between two vectors. And so what I'm going to remind you is that A dotted with B is equal to length of A, length of B, cosine theta. But I'm interested in A cosine theta. So what I'm going to do is I'm just going to solve for A cosine theta, and I'm going to say that gives me length of A cosine theta is going to equal A dotted with B divided by the length of B. Okay. And that's going to be the value of K, right? That's going to be the length of the projection is going to be this thing. So I'm just going to kind of substitute on that. But I also know that the projection of A onto B is really just like a scaled up or scaled down version of B, right? If this was all of B right here, the projection of A onto B was just like part of B. And in the case where I showed you they were sitting in an obtuse angle, it was a negative multiple of B. So really what we need to do is we're going to scale up the unit vector in the direction of B by that K value, that length of the projection. So the projection itself, the projection of A onto B, which is just some scaled up version of B. How we find a scaled up or scaled down version of B is we take the unit vector in the direction of B and we hit it with its scaling factor. So that'll be A dotted with B divided by the length of B. But then I'm going to actually apply a nice formula that we have where, right here I'd have 2 copies of the length of B. And so I've shown you this before, that the length of B squared is equal to B dotted with B. Okay. So I'm going to actually make that substitution, and this is going to be the formula for projection that I'm going to want to use today. So it's going to be A dotted with B divided by B dotted with B multiplied by vector B. I think it's important for me to point out that this thing here that I'm highlighting in gray, this is just a number, right? Because the dot product of 2 vectors is a scalar, and we're taking the ratio of 2 dot products. So that's like the number that I'm going to be multiplying b by when I compute that projection. But what does projection have to do with finding an orthonormal basis? I'm realizing I haven't even told you what an orthogonal or an orthonormal basis is. Okay, so we've got a basis for some kind of subspace that is made up of p vectors. We would say that B is an orthogonal basis if xi orthogonal to xj for each I and j less than or equal to p. Right? If all of the vectors in the basis are orthogonal to each other, then it's an orthogonal basis. And a basis is going to be orthonormal if it's orthogonal, first of all. That's the ortho. And the length of each vector in the basis is 1. So all of the basis vectors are unit vectors. And so I would say the length of xi is equal to 1 for each I. Okay. And to draw you a picture, we know, say, a basis for three-dimensional space, because that's something I can generally draw. If we can draw three that are linear independent, okay, I'm supposing those are kind of like, making an xy plane, and maybe there we've got something that's not on their span. That's going to make a basis for R3. Okay. It's not going to probably be a very great basis, because, they're not orthogonal to each other. We think about IJK, the natural basis, we really like those. We like them because they've kind of separated out into x, y, and z components, and they're units, they're ones. Okay? And we don't really think a whole lot about why that's such a good basis, but that's really what it is. So an orthogonal basis would be if I had three that were all orthogonal to one another. Like, I suppose these are kind of like laying in a plane like that. But it wouldn't necessarily be orthonormal if they all had different lengths. An orthonormal basis is going to be where we're going to have vectors all orthogonal to each other and all length 1. Okay? And the Gram-Schmidt process is going to help us go from a basis like this to a basis like that to an orthonormal basis. Now, before I actually compute one of these Gram-Schmidt orthogonalization processes, I need to kind of justify the formula for you. Otherwise, you're just going to be like, where did this come from? Why would you do that? And why would I ever need to do this? Okay. And so what I'm going to start with is how to take two vectors that are not orthogonal and work them so they become orthogonal. Okay, so the idea here is that I want to have x1, and maybe I'll call this one y1. This is an orthogonal vector to x1. And what I'm going to point out to you is that we can find y1 by taking x2 and subtracting the projection of x2 onto x1. Let's call that the projection. And in case you can't see why that's true, notice that the projection plus y1 is equal to x2. So that y1, if I'm hoping to find that orthogonal vector, is going to be x2 minus the projection that I'm talking about, the projection of x2 onto x1. Okay. And maybe I'll write down a formula for that. Right, we could use our shiny new projection formula, and we could compute it like that. But the idea is, this is how we're going to generate ourselves an orthogonal vector, is by subtracting away a projection. That's a big idea. All right, now let's bump the dimension up a little bit. And let's suppose we've got three vectors that two of them are coplanar, and so the third one is off the span of y1 and y2. Okay, and I want to find out how to get one that's a vector, instead of x3, maybe I'll call it y3, that's orthogonal to both y1 and y2. And I don't think it's too hard to see that a good option for that would be this vector right here. Say maybe that's the spot right below x3 on the plane. arrow to make it look like a vector. I'm going to call that y3. And I'm going to show you how to compute y3. What I'm actually proposing is that it's going to be, let me see what color I used when I did this last time. Yeah, I used blue. And so really what I wanted is, I've got this vector, and I'm just going to call it a. And I want to take x3, and I want to subtract away a from it to get y3. So I'll say y3 is equal to x3 minus that a. Okay. But what a actually is going to be the sum of the projections of x3 onto y1 and onto y2. So let me hopefully draw you a picture of that. Let's draw a picture of the projection of x3 onto y1 in green. And then I'm going to draw a picture of the projection of x3 onto y2. And it looks like that this is actually, it's pretty close to exactly y2 based on just the way it's working out. But that's fine. Projection is about there. And that a is equal to the sum of the projections. Maybe I'll just actually draw it like that. And that wasn't the best. That was supposed to be a parallelogram. So maybe I kind of missed the mark on the edge of this one. Maybe it's more like that. And I'll try one more time to make it look right. Like that. Okay, that's about as close as something like we get. So what I'm saying is that, yeah, if I add the first one, the projection of x3 onto y1, again, add it to the projection of x3 onto y2, then I would have, a equaling the first projection of x3 onto y1, forget my shorthand, and then I'm going to add the projection of x3 onto y2, and then my formula for y3 would be x3 minus the sum of these two projections. So I'm going to subtract both of the projections. The projection of x3 onto y1 minus the projection of x3 onto y2. And this is becoming the Gram-Schmidt algorithm. So that process I kind of just drew you some pictures of. That's going to really be the Gram-Schmidt process. And so that's just going to take us from this first basis of x vectors, which is just going to be any old basis. And then we're going to do the Gram-Schmidt algorithm on it, and we're going to get a new basis, a basis made up of y vectors, that will be an orthogonal basis. But I'm actually going to be interested in, getting eventually to an orthonormal basis. But I know that if I've got a set of vectors and they aren't unit vectors and I want to suddenly make them unit vectors, it's not terribly difficult. I just need to divide by the length. And so that'll be kind of the last step, is that I'll get down to, a third basis, z1, z2, up to, whoops, I meant to say yp. Because in general, we say that there's p vectors in a basis to say that it's dimension p. Okay, it's going to be the same number of vectors. And this will be an orthonormal basis. And the thing that we're going to do to get from basis 2 to basis 3 is we're just going to divide by lengths. Because we know that the unit vector in the direction of y1 is going to be y1 divided by the length of y1. So that's going to be the process we'll take. And I'll do an example now. All right, so the first example I've got is a basis for the yz plane. right? The YZ plane is all the points in three-dimensional space where x is equal to 0. And these two vectors are in the YZ plane, clearly, because x is equal to 0. And they are not an orthogonal basis, because if you dot those two vectors, you'll get 0 plus -1 plus 9, which is not 0. And it's not an orthonormal basis either, because, well, those are not unit vectors. Okay? So I'm going to do kind of the Gram-Schmidt algorithm. Now, always the first step is y1 equals x1. Okay, so I'm just going to let this be x1 and x2, just the order I see. That's fine. Okay, y1 is going to equal x1, because really the general formula, which I forgot to show you, here you go. Yeah, so the nth orthogonal vector is going to be the nth vector in the original set minus a series of projections, minus all the projections of xn onto the previous ones that I've already done. Okay, so if I'm starting with x1 and I'm trying to get y1, it's just got to be orthogonal to everything that came before it. But nothing came before it, so there's nothing to be orthogonal to, so we just let y1 equal x1. I'm going to kind of rearrange this. All right, that's better. And so y1 is going to equal x1, and y2 is going to equal x2 minus the project x2 onto y1. Okay? So that's going to be 0, -1, 3 minus the projection of x2 onto y1. Okay, I'll bring the projection formula back. And so if I'm projecting x2 onto y1, I will need to dot x2 and y1, so that will be 8 divided by y1 dotted with y1 is 0 plus 1 plus 9 is 10 times, what's going to happen here, times y1. Okay, so y1 is 0, 1, 3, and that's going to be 0, -1, 3 minus 0, 0.8, and 2.4. And I'm going to just need some more room, I think. And that's going to equal 0 minus 0 is 0. -1 minus 0.8 is -1.8. And 3 minus 2.4 is 0.6. Okay. And that's going to be y2. Okay, I've got y1 equaling 0, 1, 3. So now I've got orthogonal vectors. Here, maybe I'll rewrite y1 is 0, 1, 3. Having pen problems here. And y2 is going to be that. You can check and make sure that those are going to be orthogonal, but they are, because -1.8 plus 1.8 is 0. Okay. Now, actually determining, the squares of -1.8 and 0.6 is not going to be that easy. So one trick that you can employ is you can actually scale these things up or down. And I think what I'm going to do is I'm going to actually multiply y2 by 5 before I go to find its length to get the unit vector. So I'm going to say -1.8 times 5. What is that? That's going to be -9. Okay, so I'm going to just scale it up to eventually scale it down. And then 0.6 times 5 is going to be 3. And see, it's in the same direction, right? Because, y3 is -1/3 of y2. Or, pardon me, the third component is -1/3 of the second component. That was confusing. I don't know why I would call that y3. Anyway, so what I need now is to turn these into unit vectors. And so in red, I did the Gram-Schmidt algorithm. Now I'm going to turn these into unit vectors. Well, the length of y1 equals the square root of 10. And the length of y2, or really y2 prime, I guess, because I changed it a little bit, is going to be the square root of 81 plus 9 is 90. And see, that'll be much easier to work with. So my orthonormal basis is going to be z1 and z2, where z1 equals y1 divided by the square root of 10. So that's 0, 1 over root 10, and 3 over root 10. And z2 is going to equal y2 divided by the square root of 90. So 0, negative 9 over root 90, and 3 over root 90. Okay. And, well, that's a good example of one where you start off with 2 vectors. Or where we start off with 3 vectors, but that'll be it. Right, here is a basis for R3. And I'm going to just call these kind of like x1, x2, and x3. Okay, and I'm going to apply the Gram-Schmidt algorithm to turn these vectors into an orthonormal basis for R3. So the first step is going to be y1 equals x1, which is 1, 1, 1. Okay. y2 is going to equal x2 minus the projection of x2 onto all the y vectors before it, which would just be y1. So x2 minus the projection of x2 onto y1. Now that's going to be x2 is 645 minus, okay, I'm going to need to dot x2 and y1. So 645 dotted with 1, 1, 1 is going to be 6 plus 4 is 10 plus 5 is 15. Divided by y1 dotted with y1 is 1 times 1 plus 1 times 1 plus 1 times 1 is going to be 3 of y1. Okay. So that's going to be 645 minus the vector 15 divided by 3 is 5. And I'm going to be left with a 1, a negative 1, and a 0. Then y3 is going to equal x3 minus the projection of x3 onto all the ones that came before it. So the projection of x3 onto y1 minus the projection of x3 onto y2. All right, well, we can do that. x3 is 3, 6, 9. Minus, all right, the projection of x3 onto y1 is I'm going to have to dot 3, 6, 9 with 1, 1, 1. So that'll be 3 times 1 plus 6 times 1 plus 9 times 1 is going to be 18. Divided by y1 dotted with y1. I already did that once, and that was 3. And I know what y1 is. It's 1, 1, 1. Then I'll subtract the projection of x3 onto y2. And, you know, just so you remember, I'm going to highlight y2 in gray right there. So that's what I need to be projecting onto. And that's going to be, okay, so I'll dot x3 with y2. That'll be 3 times 1 plus 6 times negative 1 is negative 3. Divided by, let's see, y2 dotted with y2 is going to be 1 times 1 plus negative 1 times negative 1 is going to be 2. Okay. So this is going to be, you just got to be a little careful with the arithmetic here. 3, 6, and 9 minus 6 and 6 and 6. Wait, whoa. Minus plus 3 halves of what? And that's going to be tough to fit in here, but I think I can do it. I'm up to it. 1, negative 1, and 0. Yeah, I'm good. Minus that plus 3 halves of what I'm looking at, so I'm going to use some decimals here to make my own life a little easier. Negative 1.5 and 0. And I'm going to do this one component at a time. I'm going to say that 3 minus 6 is negative 3 plus 1.5 is negative 1.5. Then 6 minus 6 plus negative 1.5 is going to be negative 1.5. And then 9 minus 6 plus 0 is equal to 3. And that's great, but this is just an orthogonal basis I've got, y1, y2, and y3, and I need an orthonormal basis, and I need more room. So I'm going to clear out all these computations that I've done, so if you need to pause and have a look at them, the things that I'm going to be keeping are going to be the highlighted in gray vectors. Okay. And then, the rest of the actual computation work is going to go away. Now, to obtain an orthonormal basis, I'm going to say, all right, z1 equals y1 divided by the length of y1, which is going to be 1 over root 3, 1 over root 3, 1 over root 3. Because the length of y1 is going to be root of 1 squared plus 1 squared plus 1 squared. Okay. z2 is equal to y2 divided by the length of y2, which is going to be, the length of y2 is going to be the square root of 1 squared plus negative 1 squared, so it'll be square root of 2. And then z3 will be, what will z3 be? Oh, it's going to be over here. And I'm going to use that same trick I did before. I'm going to just kind of make a new vector out of doubling all of these. So that'll be -3, -3, 6. So z3 is going to be, if I took the length of y3, my adjusted y3, I'd have 9 plus 9 is 18, plus the square of 6 would be 36. In total, that's 54. So I've got -3 divided by root 54, -3 divided by root 54, and then positive 6 divided by the square root of 54. And then I could say that my orthonormal basis for R3 that I obtained by Gram-Schmitting the set x1, x2, x3 is going to be this z1, z2, z3. All right, now thank you for watching all the way with me. This was a pretty long video for linear algebra, and the Gram-Schmidt algorithm is computationally pretty intensive, especially when compared to some of the other stuff that we do in this class. But I think you could also see that it's definitely the type of thing we could teach a computer how to do, and it would be able to do really fast and really well, very accurately. This is very, arithmetic error prone. But calculators and computers, they're not so error prone in that way. And, if you're interested in the uses of the Gram-Schmidt orthogonalization process, I'd encourage you to, consult with the internet to look at that. Because I'm just showing you how to compute these things. And I have resources available to show you about the meanings of these things if you ask. But I feel like, what I have to offer in my videos is, support on the computation side. So thanks for watching. If you want to get good at Gram-Schmidt, you just need to crunch out a few examples, and then you'll get it, and it'll be fine.